The technological story of Rome does not begin with marble temples, triumphant arches, or mighty aqueducts. It begins with a way of thinking, a disciplined, practical, and relentless mindset that viewed the world not as something to admire, but as something to organize, control, and transform. From its earliest formation, Rome understood that power was not sustained by warriors alone, but by systems, and those systems were built through technology. Long before Rome became an empire, it was a small settlement struggling for survival along the banks of the Tiber River, surrounded by unpredictable terrain, rival tribes, and constant threats. The early Romans quickly learned that survival required structure. Improvisation was not enough. Order, planning, and long-term strategy became essential. Over time, the survival instinct evolved into a sophisticated ideology that civilization itself could be engineered. Unlike cultures that pursued knowledge for spiritual transcendence or philosophical contemplation, Rome pursued knowledge for function. Roman innovation was practical, repeatable, and scalable. Every advancement was measured by its ability to strengthen the state, extend control, and maintain stability. Roads were not built for beauty. They were built for movement. Bridges were not designed for ornamentation. They were designed for conquest. Water systems were not luxuries. They were instruments of population control and urban health. From the Etruscans, Rome absorbed early building techniques, drainage concepts, and structural insights. From the Greeks, it inherited geometry, architectural theory, and scientific logic. But Rome did not merely copy. It transformed. This borrowed knowledge was reorganized into a uniquely Roman doctrine: technology as governance. Engineering became another branch of administration, as essential as law or military strategy. The Roman engineer was not simply a craftsman. He was a planner, a strategist, and a guardian of imperial order. His role extended beyond construction into the realm of logistics, measurement, and systems design. Roman education for technical specialists included geometry, material knowledge, terrain analysis, and structural calculation. These men formed the backbone of Rome's expansionist capacity, enabling armies to cross rivers, build camps overnight, erect fortifications, and reshape territories in Ottoman domains. Asterisk at the heart of this transformation stood standardization. Rome understood that for an empire to function, consistency was essential. Measurement systems were regulated. Construction principles were codified. Surveying tools such as the gramma and chorobates allowed engineers to impose perfect lines upon uneven land. Entire provinces were mapped and organized into grids, defining a visual and physical manifestation of Roman authority. The Roman mindset believed that permanence was the ultimate expression of power. Temporary solutions were failures. Every structure was designed with the future in mind. This is why Roman architecture survived where others collapsed. Stone, concrete, and mortar were chosen not for appearance, but for endurance. The philosophy was clear: a structure that outlives generations becomes a symbol of eternal dominance. Roman technology also integrated deeply into administration. Census systems, grain distribution logistics, military supply chains, and urban zoning all relied upon technological planning. Cities became organized machines, regulated ecosystems where water, waste, transport, and human movement were controlled with calculated precision. The Roman city was no longer organic. It was engineered. This early technological awakening marked a pivotal moment in history. For the first time, innovation was institutionalized at a state level. Rome did not depend on isolated genius. It built systems of knowledge transmission, apprenticeship networks, military engineering schools, and state-sponsored construction units ensured continuity and expansion of technical expertise. As Rome grew, so too did its technological ambition. Hills were leveled, valleys were bridged, rivers were redirected. Nature itself was reshaped to serve the imperial vision. The Roman world was no longer limited by geography. It dictated geography. This opening chapter defines the essence of Roman technological consciousness, a civilization that transformed knowledge into power, engineering into empire, and practicality into immortality. From this foundation would rise the roads, aqueducts, fortresses, and urban marvels that would dominate the ancient world for centuries. Rome had awakened, and with it, a technological force unlike any humanity had ever seen. The Roman road system stands as one of the most sophisticated transportation networks ever conceived in the ancient world. A vast circulatory grid that allowed the empire to breathe, expand, and maintain control over territories stretching from Britannia to Mesopotamia. These roads were not chaotic tracks carved by repeated footsteps. They were deliberate, engineered structures designed for efficiency, endurance, and strategic dominance. They formed the physical backbone of Roman power, enabling swift movement of legions, rapid communication, stable commerce, and administrative cohesion across thousands of kilometers. The Roman philosophy of mobility was absolute. Nothing within the empire should be unreachable. To achieve this, Roman engineers carved roads through mountains, drained marshlands, filled valleys, and bridged rivers with uncompromising precision. Straightness was not aesthetic preference, it was doctrine. Roman roads often cut directly across landscapes, ignoring natural curves in favor of efficiency and speed, embodying an ideology that geography itself must submit to imperial will. Each road was constructed according to a strict engineering hierarchy. The process began with detailed surveying, using specialized tools to ensure perfect alignment. Once the route was mapped, the ground was excavated to create a stable foundation. Multiple layers were then laid with meticulous care. The lowest layer, the statumen, consisted of large stone slabs forming a solid base. Above it lay the rudis, a mixture of crushed stone and lime that provided structural support. The nucleus followed, composed of fine gravel and mortar, compacted to create a smooth, stable surface. Finally, the summum dorsum, the visible road surface, was laid with tightly fitted stone blocks, slightly arched to allow water to drain toward the sides. This cambering system prevented erosion and water damage, ensuring longevity that modern roads rarely achieve. Roman roads were not built solely for military use. They were instruments of economic integration. Traders, messengers, government officials, and civilians moved along these highways, creating a unified imperial economy. Way stations, known as mansions, provided rest, food, and lodging, while mutations allowed for the rapid exchange of horses, creating an early form of express communication network. Couriers of the cursus publicus could travel extraordinary distances in remarkably short times, enabling centralized authority and efficient administration. Bridges played a crucial role in the mobility system. Roman bridge engineering relied heavily on the arch principle, distributing weight efficiently across stone structures. These bridges were often constructed using opus caementitium foundations and stone superstructures, allowing them to withstand floods, heavy loads, and the relentless passage of time. The Alcantara Bridge in Spain and the Pons Fabricius in Rome stand as lasting symbols of this mastery. A river transport complemented road networks, forming integrated logistical systems. Large barges and cargo ships traveled along the Tiber, Rhine, Danube, and Nile, transporting grain, stone, military supplies, and goods. Harbors were fortified and engineered with breakwaters, lighthouses, and docking systems that facilitated maritime trade while protecting fleets from storms and enemy attacks. Ports such as Ostia and Puteoli became bustling economic arteries feeding the imperial capital. Roman transportation extended beyond earth and water into mechanical innovation. The development of wheeled transport vehicles designed specifically for Roman roads revolutionized cargo movement. Wagons were engineered with reinforced axles and iron rims to withstand stone surfaces. The cursus vehicularis introduced specialized carts for military transport, administrative use, and civilian trade, each designed for specific functional requirements. The strategic implications of this mobility network were immense. Roman legions could march with unprecedented speed, establish fortified camps within hours, and maintain supply chains across vast distances. This capacity for rapid deployment turned Rome into a military superpower, whose response time crushed revolts and discouraged rebellion. Beyond war, the psychological effect of Roman roads was equally powerful. These stone ribbons symbolized inevitability. Their presence reminded conquered peoples that Rome was permanent, organized, and omnipresent. The The road was a silent message etched into the land. Rome is here. Rome endures. The Roman transportation system transformed space itself. Distance no longer meant isolation. Provinces once separated by natural barriers became interconnected components of a single imperial machine. Goods, ideas, cultures, and people flowed along these pathways, accelerating cultural exchange and economic integration at a scale previously unimaginable. In constructing these networks, Rome redefined movement as control and control as civilization. The empire's ability to dominate terrain through engineered mobility formed one of the most critical foundations of its success. Roads did not merely connect cities. They connected power to presence and presence to permanence. As the empire expanded, so too did the complexity of its transportation systems, evolving into a sophisticated logistical organism that powered everything from military conquest to daily urban life. This mastery of movement would soon be complemented by another extraordinary achievement: control over water itself. If Roman roads represented mastery over land, aqueducts represented something even more profound: domination over one of nature's most vital and uncontrollable forces, water. No civilization before Rome had ever constructed such extensive, precise, and reliable water management systems across such vast distances. Through aqueducts, Rome transformed water from a natural element into a regulated, engineered lifeline that sustained millions and reshaped the concept of urban living. Roman hydraulic engineering was not an aesthetic endeavor. It was a physiological necessity for empire. Clean water meant health. Health meant population stability. Stability meant power. Thus, every aqueduct was both an engineering structure and a political instrument, reinforcing Rome's authority through the simple act of making life possible. The Roman approach to water conveyance was based on an extraordinary understanding of gravitational flow. Aqueducts were designed with a minute but consistent gradient, often declining only a few centimeters over kilometers, ensuring a smooth and continuous current. Such precision demanded advanced surveying, mathematical calculation, and an intimate understanding of terrain. The slightest miscalculation could disrupt an entire system. Yet Roman aqueducts functioned reliably for centuries. Water sources were typically drawn from remote springs or mountain streams, purified naturally by distance and filtration, and then channeled toward cities through a combination of underground tunnels, stone conduits, and towering arcades. While popular imagery associates aqueducts with monumental arches, the majority of their course often ran underground, protected from contamination and evaporation. Only when necessary, to cross valleys or uneven terrain, did they rise above ground in elegant, rhythmic arches. Iconic aqueducts such as Aqua Appia, Aqua Claudia, Ennio Novus, and the monumental Pont du Gard demonstrate not only technical brilliance, but also aesthetic harmony. These structures were simultaneously functional machines and grand architectural statements, projecting Rome's image as a civilization that commanded both nature and design. Once water reached the city, it entered an intricate distribution network. Lead, terracotta, and stone pipes carried water to public fountains, bath complexes, private residences, and latrines. Flow was controlled by valves and reservoirs known as castellum divisorium, which regulated pressure and allocated supply across districts. The system ensured that even densely populated urban centers maintained continuous access to clean water. The impact on public life was revolutionary. Roman bathhouses, the thermae, became not only places of hygiene, but centers of social interaction, intellectual discussion, and relaxation. These massive complexes, supplied by aqueduct systems, relied heavily on precise water regulation and heating mechanisms to operate pools of varying temperatures simultaneously. Equally significant was Rome's approach to waste management. Through interconnected sewer systems, most famously the Cloaca Maxima, wastewater was carried away from populated areas into rivers, preventing stagnation and the spread of disease. This integrated approach to sanitation placed Rome centuries ahead of many future civilizations. In terms of public health infrastructure, Roman hydraulic engineering also extended to agriculture. Irrigation channels transformed previously arid land into fertile farmland, increasing food production and supporting the empire's expanding population. In rural estates, water-powered mills utilized controlled flow to grind grain, representing an early form of renewable mechanical energy that reduced dependence on manual labor. The intellectual depth behind these systems cannot be overstated. Roman engineers studied water pressure, sediment accumulation, slope resistance, and flow velocity with remarkable sophistication. Maintenance protocols were established, inspection teams were employed, and repair schedules were enforced, all evidence that these systems were not temporary achievements, but permanent institutions. By harnessing water on such a scale, Rome achieved more than comfort or convenience. It created a living environment where cities could grow exponentially, populations could thrive, and urban life could evolve into a complex, dynamic organism sustained by invisible technological veins flowing beneath stone streets. Water became Rome's silent empire within the empire, an unseen force shaping civilization from beneath. Governed by precision, discipline, and unparalleled engineering mastery, with land and water firmly under control, Roman innovation would now turn toward transforming matter itself, redefining architecture through a revolutionary material that would alter construction history forever. Asterisk. If Roman roads conquered distance and aqueducts mastered water, Roman concrete conquered the very limitations of matter itself. With the invention and perfection of opus caementitium, Rome initiated a structural revolution that would redefine architecture for millennia. This material was not merely a construction aid. It was the foundation of an entirely new architectural philosophy, one that liberated builders from the constraints of traditional stone and brick, allowing forms, scales, and spatial concepts previously unimaginable. Roman concrete emerged from a sophisticated blend of volcanic ash, pozzolana, lime, water, and aggregate. Unlike modern concrete, which often deteriorates with time, Roman concrete displayed an astonishing self-strengthening property, especially when exposed to seawater. The chemical reaction between lime and volcanic minerals created crystalline bonds that increased durability over centuries. This innovation allowed Roman structures to endure earthquakes, environmental stress, and the relentless passage of time with unparalleled resilience. This material enabled a radical transformation in architectural form, where earlier civilizations relied on post-and lintel systems that limited spatial dimensions. Rome introduced sweeping arches, massive vaults, and domes that defied gravity itself. Structures no longer had to be supported by dense clusters of columns. Space could open, expand, and breathe. Architecture shifted from rigid geometry to dynamic volume. The Pantheon stands as the ultimate testament to this revolution. Its colossal dome, spanning over 43 meters, remains the largest unreinforced concrete dome in the world, rising in perfect harmony. Its diminishing aggregate density toward the apex demonstrates an extraordinary understanding of load distribution and material optimization. The oculus at its center not only serves an aesthetic purpose, but also reduces structural stress, revealing a sophisticated fusion of engineering and symbolism. Beyond sacred monuments, Roman concrete reshaped every facet of urban life. Amphitheaters like the Colosseum, basilicas, bath complexes, warehouses, and insulae multi-story apartment buildings all relied on this material's extraordinary versatility. Entire neighborhoods could now be constructed quickly, efficiently, and at scale, facilitating the exponential expansion of Roman cities. Roman architectural design was inseparable from technical logic. Load paths were calculated implicitly through empirical testing. Engineers understood compression, tension, and shear forces long before modern structural theory was formalized. Vaulting systems such as barrel vaults, groin vaults, and domandrum configurations demonstrated nuanced control over weight transfer and spatial stability. The aesthetic implications of this technology were profound. Monumentality became a visual language of power. Massive arches and soaring domes symbolized Rome's dominance over physical reality itself. Architecture was no longer just shelter. It was ideology in stone and concrete, a declaration of imperial permanence visible across horizons. Standardization once again played a central role. Construction principles were codified and replicated throughout the empire, A temple in Asia Minor adhered to the same structural logic as one in North Africa. Roman architectural identity transcended geography, unifying diverse territories under a single visual and structural system. Builders employed wooden formworks, scaffolding systems, and lifting machines to mold and place concrete precisely. Cranes powered by human or animal labor raised heavy elements to unprecedented heights. This orchestration of material, labor, and mechanical innovation transformed construction into a disciplined science. The psychological impact of these structures must not be underestimated. To stand beneath a Roman dome or walk through the grand corridors of an imperial basilica was to witness power made physical. These spaces were designed not only for functionality but for awe, reinforcing the spiritual and political dominance of Rome through scale alone. Even today, modern engineers study Roman concrete with fascination, seeking to replicate its longevity and ecological efficiency. Its low-carbon composition and extraordinary lifespan present lessons for contemporary sustainable architecture, proving that ancient innovation still surpasses modern convenience. With the mastery of matter achieved, Rome extended its engineering genius toward another domain, the art of war, transforming conflict into a calculated science backed by mechanical innovation and strategic precision. Roman military dominance was not achieved through bravery alone. It was built upon a foundation of engineering precision, technological innovation, and systematic logistical mastery that transformed warfare into a calculated science. The Roman army was not merely a fighting force, it was a mobile construction empire, capable of reshaping landscapes, erecting fortified systems, and deploying mechanical power with ruthless efficiency. At the core of this superiority lay Rome's unparalleled military engineering tradition. Roman warfare was defined by preparation. Before a single blade was drawn, Roman engineers altered the battlefield. Fortified camps, siege platforms, defensive walls, roads, bridges, and logistical corridors were constructed with astonishing speed and accuracy. Each legion carried specialized engineering units known as fabri, responsible for every technical aspect of military operation. These men were trained not only in combat, but in structural design, mechanics, and terrain analysis, making them as critical as any commander. One of Rome's most formidable innovations was the standardized fortified camp, or castrum. At the end of each day's march, legions constructed a complete military settlement featuring defensive ditches, ramparts, wooden palisades, and watchtowers. These camps followed precise geometric layouts, ensuring efficiency, order, and rapid deployment. By morning, the Roman army was protected by a temporary fortress, a concept unmatched by any contemporary force. Siege warfare represented the pinnacle of Roman mechanical ingenuity. Roman engineers developed a terrifying arsenal of siege machines designed to break walls, crush morale, and dominate fortified cities. Among the most formidable were the ballista, a massive torsion-powered crossbow capable of launching heavy projectiles with devastating accuracy. The onager, a stone-throwing catapult that pulverized fortifications, and the battering ram, encased within mobile protective structures to breach walls under continuous assault. These machines were not crude tools. They were finely calibrated instruments of destruction, requiring mathematical precision and mechanical understanding. Torsion systems utilized twisted ropes made of sinew or hair to store enormous energy, which could be released with devastating force. Engineers calculated angles, distances, and impact trajectories to maximize effectiveness, marking one of the earliest forms of applied military physics. Roman battlefield tactics were also deeply technological. The iconic testudo formation, where soldiers locked shields overhead and in front to create an armored shell, demonstrated tactical engineering at the human level. This living machine allowed legions to advance under projectile fire, approaching enemy fortifications with near impenetrable protection. Logistical engineering ensured that armies remained supplied across vast distances. Roads were reinforced for troop movement, temporary bridges were constructed to cross rivers, and mobile supply depots maintained continuous flow of weapons, food, and water. Roman military campaigns functioned as precision systems, where every component, from weapon to transport, operated in coordinated synchronization. Naval warfare also benefited from Roman engineering principles. Warships were reinforced with ramming prows, modular rowing systems, and reinforced hull designs. Mechanical boarding bridges such as the Corvus allowed Roman forces to transform sea combat into close-quarters infantry conflict, leveraging their land combat superiority even at sea. Military architecture expanded beyond battlefields into permanent defensive infrastructures. Fortresses, watchtowers, border walls, and fortified cities defined the edges of the empire. The most famous example, Hadrian's Wall, represented an integrated system of surveillance, logistics, and defense engineering that regulated movement and maintained control across volatile frontiers. Psychological impact was as vital as physical destruction. The sight of Roman siege towers approaching a city's walls instilled terror long before contact. The mechanical precision, relentless coordination, and systematic efficiency of Roman war machines projected inevitability. The sense that resistance was futile against such overwhelming technological might. Through the mechanization of war, Rome transformed conquest from chaos into choreography. Conflict became controlled, systematic, and repeatable. Military engineering evolved into a doctrine, a deliberate science of domination, ensuring that Rome's territorial expansion was not temporary conquest, but permanent control. With warfare engineered into predictable systems, Rome next turned its gaze inward, focusing on the perfection of civilian life through urban design, sanitation, and daily infrastructure, transforming cities into living machines of order and efficiency. With military dominance secured and monumental architecture perfected, Rome turned its technological mastery inward, focusing on the orchestration of daily life within its cities. Urban planning under Roman rule was not incidental growth but a calculated engineering strategy. Designed to create order, efficiency, and control, the Roman city was conceived as a living system where every street, structure, and utility served a defined function in the grand mechanism of imperial life. Roman urban design followed strict geometric principles. Cities were laid out according to a grid structure, centered around a primary axis, the Cardo Maximus running north to south, and the Decumanus Maximus running east to west. Their intersection formed the heart of the city. The Forum, a multifunctional space that combined political authority, commercial activity, and social interaction. From this core radiated an organized network of secondary streets, dividing the urban space into manageable, functional blocks. This discipline in layout allowed Roman cities to be replicated across the empire with remarkable consistency. Whether in Gaul, Britannia, North Africa, or the Levant, Roman urban centers exhibited the same structural logic, reinforcing a shared imperial identity and facilitating administrative efficiency. This universality enabled rapid governance, standardized construction, and predictable infrastructure deployment. Sanitation represented one of Rome's most advanced contributions to urban life. Far beyond basic sewage channels, Rome developed complex drainage networks that carried waste away from populated areas, reducing disease and maintaining public hygiene. The most legendary of these systems, the Cloaca Maxima, institutionalized waste management at a scale that would not be matched again for centuries. Wastewater flowed through stone-lined channels beneath the streets, powered by gravity and connected to the Tiber River, preventing stagnation and unsanitary conditions. Public latrines were interconnected with this sewer system, designed with flowing water beneath seats to carry waste away continuously. These facilities were communal and efficient, reflecting both practical engineering and social norm. Cleanliness was not only a cultural value but a technological mandate. The hypocaust system further exemplified Rome's capacity to engineer comfort. This underfloor heating technology circulated hot air produced by furnaces through hollow spaces beneath floors and within walls. Used extensively in bathhouses and elite residences, hypocaust systems turned Roman buildings into climate-controlled environments, a level of domestic comfort unprecedented in the ancient world. Bath complexes, the thermae, represented the pinnacle of urban technological integration. These massive facilities included hot, warm, and cold pools, ventilation systems, water circulation channels, and intricate heating mechanisms, all operating simultaneously in carefully calibrated equilibrium. These spaces served not only as hygiene centers, but as social hubs, blending engineering excellence with cultural life. Roman insulae, or multi-story apartment buildings, demonstrated early forms of vertical urban living. Constructed using concrete and brick, these structures housed large segments of the urban population, revealing Rome's efforts to engineer density and accommodate growing demographics. Though often utilitarian, their existence marked a sophisticated approach to spatial efficiency and population management. Street infrastructure was equally advanced. Paved roads within cities featured raised sidewalks, drainage channels, and pedestrian crossings. Milestones, directional markers, and urban signage guided movement, reinforcing Rome's vision of structured flow and regulated space. Public lighting through oil lamps further extended functionality into night hours, lengthening productive time and enhancing safety. Urban supply systems operated with logistical precision. Markets, warehouses, and granaries were strategically placed to ensure constant distribution of food and goods. Grain supply operations were supported by maritime transport, storage engineering, and currency regulation, exemplifying the integration of economy and infrastructure. The Roman city was therefore not an organic sprawl, but a designed environment. Every element functioned within a coordinated network, supporting health, efficiency, surveillance, and control. Through urban engineering, Rome created spaces that transcended habitation. They became manifestations of power, rationality, and technological supremacy. This transformation of daily life into an engineered system marked a fundamental shift in civilization. Rome demonstrated that technology could shape not only landscapes, but also habits, behaviors, and social rhythms. Life itself could be structured, optimized, and regulated through intelligent design. With urban life engineered into precision, Rome now extended its technological capabilities into the realm of production, extraction, and large-scale industrial organization, establishing economic systems that fueled the empire's vast reach. As Rome perfected its control over land, water, architecture, warfare, and urban life, it turned its technological vision toward the heartbeat of imperial sustainability, production. The Roman economy was not sustained by trade alone, but by a vast, technologically driven system of extraction, manufacturing, and organized labor that transformed raw resources into the material foundation of empire. In this domain, Rome approached industry not as scattered craftsmanship, but as a coordinated, large-scale mechanism operating with remarkable efficiency and precision. Roman industrial power began in the earth itself. Mining operations throughout Hispania, Britannia, Dacia, and the eastern provinces supplied vast quantities of gold, silver, copper, iron, tin, and lead. These resources fueled currency production, weapon manufacturing, construction, and infrastructure expansion. Mining was conducted with systematic complexity, involving deep shaft excavation, ventilation systems, drainage engineering, and mechanical extraction techniques that rivaled later medieval practices. One of the most advanced Roman mining methods was hydraulic mining, known as hushing. Large volumes of strategically stored water were released suddenly to erode soil and rock, exposing mineral veins beneath. This technique demonstrated Rome's mastery over both geology and fluid mechanics, allowing rapid excavation on a scale unseen in earlier civilizations. At sites such as Las Medullas in Spain, entire mountains were reshaped through this technique, a dramatic testimony to Rome's industrial ambition. Metallurgy represented another pillar of Roman technological achievement. Ores were smelted in specialized furnaces capable of reaching extreme temperatures. Blacksmiths forged weapons, tools, agricultural implements, architectural fasteners, and household objects with precision. Iron production, in particular, supported both military expansion and civilian industry, ensuring the empire's structural and defensive resilience. Craft production extended far beyond metal. Roman workshops produced glassware, ceramics, brick, textiles, leather goods, and decorative objects at unprecedented scale. Blow-molded glass production enabled mass creation of vessels, while standardized pottery from centers such as Iridium spread throughout the empire. reflecting early forms of industrial branding and mass distribution. Brick and tile manufacturing became a regulated industry, essential for urban expansion. Bricks were often stamped with the insignia of the producing workshop or imperial estate, revealing a highly organized production identity and accountability system. The standardization ensured consistency in quality and size across vast territories, facilitating efficient construction processes. Agricultural production also evolved into semi-industrial scale through large estates, known as latifundia. These operations combined mechanical tools, irrigation systems, storage infrastructure, and logistics management to produce grain, olives, wine, and other staples in enormous quantities. The Roman grain supply, particularly from Egypt and North Africa, was an elaborate system involving transportation networks, storage silos, and distribution mechanisms that sustained the empire's massive urban populations. Transport and commerce integrated seamlessly with production. Warehouses, known as horia, stored goods in carefully engineered facilities designed to preserve temperature, prevent spoilage, and manage inventory. Harbors and shipping networks moved these products across seas and rivers, feeding the economic circulation that maintained Rome's prosperity. Labor organization was equally systematic. Slaves, freedmen, and skilled artisans operated within structured production hierarchies. While exploitative by nature, the system allowed Rome to mobilize massive workforces for sustained output. Specialized guilds or collegia regulated quality, training, and trade practices, reinforcing professionalism and continuity within crafts. Mechanical innovation further accelerated productivity. Water mills, wind mechanisms, and rotary devices reduced reliance on human labor and increased efficiency. The Barbegal Mill complex in Gaul, comprising multiple water-powered grain mills, stands as one of the first known industrial centers in history, a precursor to the mechanized factories of the modern era. Through industrial engineering, Rome transformed its economy into a machine of endurance. Resource extraction, material processing, and logistical coordination became synchronized processes fueling every aspect of life, from grand monuments to everyday utensils. Production was no longer artisan improvisation. It was systemic imperial infrastructure. This mechanized economy not only sustained Rome's military and urban systems, but also exported Roman technological influence across continents, embedding Roman standards into the daily fabric of conquered lands. As the empire mastered production and material prosperity, it expanded its technological dominance into a domain often overlooked yet crucial to imperial power: control of the seas and mastery of maritime engineering. While Roman mastery of land defined its territorial dominance, control of the sea secured its economic lifeline and strategic supremacy. The Mediterranean, known to the Romans as Mare Nostrum, our sea, became a vast engineered corridor through which grain, soldiers, materials, and information flowed with relentless efficiency. Roman naval technology transformed maritime space into an extension of imperial infrastructure. Governed by precision, mechanical innovation, and tactical engineering, Roman shipbuilding evolved from practical necessity into sophisticated design science. While initially influenced by Greek and Phoenician traditions, Roman naval architecture soon established its own identity through structural standardization, modular construction, and reinforced hull engineering. Shipyards across Ostia, Ravenna, Alexandria, and Carthage operated as advanced production centers, where vessels were built according to regulated specifications, ensuring reliability across long-distance voyages. Military vessels such as triremes and quinquiremes formed the backbone of Roman naval power. These ships were designed with multiple tiers of oars, allowing high maneuverability and speed. Their most feared innovation was the corvus, a rotating boarding bridge equipped with an iron spike. This device allowed Roman soldiers to latch onto enemy ships and convert naval combat into close-quarters infantry engagement, effectively transforming sea battles into familiar land warfare scenarios. Where Roman legions excelled, naval engineering extended beyond combat ships. Massive merchant vessels transported grain, marble, spices, and textiles across the empire. sustaining Rome's urban population and monumental construction projects. These ships featured reinforced keels, compartmentalized storage, and advanced rudder systems that enhanced stability and cargo capacity. The integration of sail and/or propulsion systems optimized navigation. Across diverse weather conditions, harbor engineering played a crucial role in maritime dominance. Roman ports were complex technological ecosystems featuring breakwaters, piers, lighthouses, cranes, and underwater concrete foundations. The harbor of Portus, near Rome, stands as a testament to this sophistication. Its artificial basins, wave barriers, and docking systems enabled safe anchorage and smooth logistical flow regardless of sea turbulence. Perhaps the most extraordinary innovation in Roman maritime construction was its use of hydraulic concrete in underwater environments. By deploying opus caementitium directly beneath water, Roman engineers built artificial harbors and foundations that resisted erosion and strengthened over time. This allowed the expansion of maritime infrastructure into previously inaccessible coastal regions, enhancing trade and military deployment potential. Navigation techniques combined empirical observation with practical astronomy. Sailors used the position of stars, coastline patterns, wind directions, and seasonal currents to chart courses. Roman nautical maps were functional, experience-based tools that facilitated wide-reaching exploration and sustained maritime logistics. Though lacking modern instruments, Roman sailors operated with remarkable precision and situational awareness. The strategic significance of naval power extended beyond commerce. Sea control enabled Rome to isolate enemy territories, secure supply routes, and expand imperial influence across islands and coastal regions. Dominance over Mediterranean waters ensured political stability and economic continuity, reinforcing the empire's technological superiority as both a land and sea power. Maritime transport integrated seamlessly with inland road systems and river routes, forming a continuous logistical web connecting the furthest reaches of the empire. Grain shipments from Egypt, olive oil from Hispania, and marble from Greece flowed through these networks with orchestrated efficiency, transforming Rome into the central hub of global exchange. Naval technology also influenced cultural and technological diffusion. Ship movements transmitted architectural styles, construction techniques, and scientific knowledge between provinces, fostering a shared imperial identity forged through movement and connectivity. Through mastery of the seas, Rome extended its technological philosophy into an entirely new domain. Water was no longer merely controlled. It was navigated, dominated, and transformed into a strategic frontier engineered to serve imperial continuity. With maritime supremacy established, Roman innovation next expanded into the realm of intellectual systems, science, medicine, and knowledge organization, solidifying its legacy not only through structures and machines, but through the systematic cultivation of human understanding itself. While the physical world of Rome was shaped by stone, concrete, and iron, an equally powerful transformation was taking place within the realm of the mind. The Roman Empire did not survive through force alone. It endured through the organization of knowledge, the discipline of science, and the systematic cultivation of intellectual structure. In Rome, knowledge was not abstract contemplation. It was a mechanism of stability, a tool of governance, and a pillar of imperial continuity. Roman scientific culture developed as a fusion of inherited Greek philosophy and distinctly Roman pragmatism. Where the Greeks sought understanding for the sake of truth, the Romans sought understanding for the sake of function. Every observation, calculation, and theory was evaluated through a single question: does this improve the machinery of civilization? Roman mathematics was not poetic speculation. It was a practical science used to measure land, align cities, distribute resources, design architecture, and regulate taxation. Surveyors employed geometric precision to define property boundaries and establish infrastructural consistency across vast territories. Angles, proportions, and distances were carefully calculated not for intellectual elegance, but for stability and efficiency. Astronomy likewise served structured purpose. Celestial observation regulated agricultural cycles, seasonal transitions, military campaign timing, and civic calendars. Roman understanding of time was synchronized with cosmic movements, creating harmony between natural order and administrative control. The empire did not simply exist within time. It organized time itself. Medicine emerged as one of Rome's most advanced scientific domains. The health of Rome's armies and citizens was considered a matter of national security. A sick population weakened the state. Therefore, healthcare became an institutional responsibility. Military hospitals known as valetudinaria were strategically placed throughout the empire, offering structured treatment for wounded and ill soldiers. These facilities functioned with remarkable organization, featuring separated areas for care, recovery, and sanitation. Roman doctors developed extensive surgical practices. Instruments crafted with precision allowed procedures ranging from wound treatment and bone realignment to surgical extraction and amputation. Scalpels, probes, forceps, hooks, and cauterizing tools reflected a level of technical sophistication unmatched by many later civilizations. Though the concept of microorganisms was unknown, Romans practiced hygiene through washing, herbal antiseptics, controlled bandaging, and disciplined wound care. Medical theory was systematized by figures such as Galen, whose observation-based approach to anatomy and diagnosis shaped medical knowledge for centuries. His work transcended Rome itself, influencing Islamic and European medicine well into the Renaissance. Roman healing moved away from mysticism toward method, logic, and procedural practice. Public health further demonstrated Rome's integration of science into infrastructure. Aqueducts delivered clean water, sewer systems removed waste, and public baths reinforced hygiene as cultural norm. Disease prevention became an engineered solution. The Roman city was not merely inhabited, it was medically structured. The Roman pursuit of knowledge extended into the natural world. Pliny the Elder's monumental Naturalis Historia documented animals, plants, minerals, climate patterns, and medicinal substances. This encyclopedic work represented one of humanity's earliest attempts to systematically record and preserve empirical knowledge. Observation was no longer temporary. It became memory. Time measurement also reflected scientific discipline. Sundials and water clocks structured daily schedules, work rhythms, legal operations, and religious ceremonies. The Roman calendar regulated agriculture, trade, and governance. Time itself was transformed from chaos into order, reinforcing the empire's culture of precision. Education operated through structured mentorship rather than formal institutions. Knowledge passed from master to apprentice, from physician to student, from engineer to trainee. This ensured continuity not through theory alone, but through practiced skill. Libraries preserved scrolls containing medical texts, architectural designs, scientific observations, and technological instructions, forming intellectual reservoirs that guarded against decay. Roman philosophy, especially Stoicism, reinforced this rational worldview. Discipline, restraint, and respect for natural law guided intellectual pursuit. The world, Romans believed, could be understood through reason and shaped through method. This conviction powered an entire civilization's technological confidence. Through the orchestration of science, medicine, and organized knowledge, Rome transformed thought into structure. Information became design. Design became system. System became empire. The Roman intellectual machine operated silently beneath the visible world of marble and steel, sustaining a civilization that endured far beyond the lifespan of its emperors. In the unseen realm of intellect, Rome achieved its most lasting triumph, the transformation of knowledge into a disciplined force, capable of shaping history itself. The Roman Empire may have disappeared as a political entity, but the technological systems it created continued to live far beyond its historical lifespan. Unlike many ancient civilizations whose innovations faded with their decline, Rome left behind structures, principles, and methodologies that became permanent components of the world that followed. Its true legacy was not confined to monuments or military domination, but embedded in the very way later societies learned to build, organize, and sustain themselves. Roman technology established a new relationship between humanity and permanence. Before Rome, construction often served immediate needs. After Rome, architecture became an expression of continuity. The concept that a structure should endure across generations reshaped the philosophy of building itself. Cathedrals, civic institutions, defensive walls, and urban centers constructed in later centuries drew directly from Roman structural logic, replicating its emphasis on durability, proportion, and calculated design. The Roman use of concrete, arches, domes, and load-distributing systems introduced forms that allowed architecture to transcend previous limitations. These principles influenced the evolution of engineering well into the modern era, forming the foundations of contemporary structural practice. From Gothic cathedrals to neoclassical government buildings and modern urban infrastructure, Roman comprehension of stability and spatial control remained a silent guide. Beyond architecture, Rome's infrastructure philosophy transformed how civilizations understood movement and connectivity. The idea that territories must be integrated through engineered networks became fundamental to political and economic stability. Modern road systems, railways, and transportation corridors reflect the same core principle once embedded in Roman design, that mobility secures unity, and unity sustains power. Urban organization likewise carries Rome's imprint. The structured layout of cities, regulation of public space, and integration of water and waste systems established a model that shaped future urban development. The Roman city was not accidental, it was planned. That philosophy continues to define modern urban environments, where order, accessibility, and functionality govern spatial design. Roman sanitation and water management introduced the principle that public health was an engineered responsibility. Clean water supply, drainage, and waste control became central components of organized living. These ideas evolved directly into modern sanitation systems, reinforcing the belief that environmental control is essential to human survival and societal stability. Even administrative systems reflect Roman influence. The structured management of resources, standardization of procedures, and systematic regulation of labor created a foundation for modern bureaucracy. Governance became organized through systems rather than solely dependent on personal authority, shaping the institutional frameworks of later states. The intellectual legacy of Roman technology also endured through preserved texts, transmitted knowledge, and inherited methodologies. Roman engineering treatises, architectural principles, and practical scientific understanding were absorbed, adapted, and expanded by subsequent cultures, ensuring the continuity of technical knowledge through periods of political fragmentation and social transformation. More profoundly, Rome altered the philosophical perception of progress itself. It demonstrated that advancement was not the result of chance, but of discipline, planning, and structured knowledge. Civilization, in the Roman vision, was something to be designed, maintained, and engineered through rational systems capable of surviving time. Although Rome ceased to exist as an empire, its technological mindset continued to shape the invisible framework of the modern world. Every engineered structure, every planned city, every organized system of infrastructure carries echoes of Roman logic, silently sustaining the mechanisms of contemporary civilization. Rome no longer rules through emperors or legions, but through the enduring systems it taught humanity to create. Its legacy persists not as memory, but as structure, a continuous presence in the foundations of the world that came after it.